The vulnerability of all metals to corrosion is a major concern for manufacturers. While metals are durable and effective, they do not always maintain a uniform finish after manufacturing, which is often preferred in consumer products. This is why surface finishing is a critical step in the production of metal components. A high-quality metal surface treatment can improve the appearance and, crucially, extend the lifespan of the finished product. There are various types of surface finishing methods, such as electroplating, anodizing, polishing, painting, and powder coating. In this video, you will learn about the anodizing process in detail, including its types, and discover how this powerful surface treatment increases durability, enhances corrosion resistance, and even adds antimicrobial properties to everyday aluminium products. Welcome to the channel. So what is anodizing? Anodizing is an electrochemical process used to treat the surface of metal components. It creates a film ranging from 0.5 micrometers to 100 micrometers on the metal surface. The name anodizing comes from the fact that the metal part being coated serves as the anode in an electrolyte bath, differentiating it from electroplating, where the part becomes the cathode. Anodizing is mainly applied to metals that form a protective oxide layer, with aluminium being the most common. Other metals suitable for anodizing include magnesium, titanium, and zinc. Unlike most protective coatings, anodizing permanently alters the outer structure of the metal. This is why it is referred to as conversion coating, distinguishing it from other coatings like painting and electroplating. For example, in aluminium, paints and platings sit on top of the surface, whereas anodizing converts the outer layer of aluminium into aluminium oxide. As a result, the coating is fully integrated with the aluminium substrate, making it resistant to chipping or flaking, unlike paint. Why do we anodize? 1. To increase corrosion resistance. The thick oxide layer generated during anodizing significantly enhances corrosion resistance. It protects the underlying metal by forming a barrier against corrosive agents. This passive film is chemically inert and does not degrade in environments with moisture or chemicals such as acids and bases. 2. To improve wear or abrasion resistance. Although pure aluminium is relatively soft and easily deformed, anodized aluminium becomes much harder due to the alumina layer, with Vickers hardness values ranging from HV200 to HV600. The oxide layer exhibits ceramic properties, providing heightened wear resistance compared to untreated aluminium. This added strength ensures that aluminium components maintain their integrity, making anodized aluminium ideal for long-term applications, such as shafts and sliding parts. 3. To enhance aesthetic appearance. Anodizing not only improves the functional properties of aluminium but also enhances its visual quality. This coating serves as the final finishing treatment when a natural aluminium appearance is desired or when a mechanically induced pattern should be preserved. The anodization process. The anodizing process involves 4 stages. Surface preparation, anodizing, coloring, sealing the anodized layer. The first step is surface preparation, which ensures that the metal surface is free from contaminants and ready for uniform oxide formation. This pre-treatment process is vital for the adhesion of the oxide layer and the overall appearance of the anodized components. Before anodizing, the aluminium surface must be thoroughly cleaned to eliminate contaminants, oxides, and machining residues. These preparations include degreasing. The aluminium is cleaned in an alkaline bath to remove oils and residues from manufacturing. Minor imperfections are addressed through etching with a sodium hydroxide solution, creating a uniform matte finish. Desmutting. Etching can leave behind a smut or deposit of alloyed metals. Desmutting removes these layers using an acid-based solution like nitric or sulfuric acid. This step is crucial before anodizing, as smut can cause imperfections or color variations in the anodized layer. The next phase is the anodizing process itself. But before we explore this stage, let's look at the various parameters that influence the anodizing process, including time, voltage, temperature, and current density. These factors control the morphology and chemistry of the anodized layer by adjusting the balance between oxide growth and oxide dissolution reactions. Time. The duration of the anodizing process affects both the film thickness and the formation of pure oxide. Longer anodizing time results in thicker coatings, enhancing corrosion resistance and wear resistance. Voltage. The voltage used during anodizing determines the speed at which the anodizing layers form. Operating at high voltage produces a thick but rough film, while anodizing at low voltage results in a thin and smooth film. Thus, lower voltages are recommended for decorative anodizing, while higher voltages are suitable for wear-resistant surfaces. Temperature. The temperature of the electrolyte bath can alter the speed of the anodizing process and the characteristics of the oxide layer. Lower temperatures, 5 to 10 degrees Celsius, tend to produce denser, thicker oxide films with better corrosion and wear resistance. In contrast, higher temperatures, 25 to 30 degrees Celsius, can lead to faster oxide layer formation initially, but the film may be looser and requires sealing to improve performance. Current density. Current density refers to the amount of electric current per unit area of the workpiece surface, controlling the rate of oxide layer growth. Higher current densities can lead to faster anodizing rates, increased film thickness, and enhanced corrosion resistance within a certain range. However, excessively high current densities can cause localized heating, leading to film dissolution, uneven coating, and reduced anodizing efficiency. Lower current densities result in a slower rate of oxide film formation, promoting uniform deposition and a thinner oxide layer. The anodizing stage. Once the metal surface is clean, the anodizing process begins. The metal part, usually made of aluminium, is submerged in an electrolytic bath containing sulfuric acid or chromic acid, depending on the desired finish. An electric current is then passed through the bath, with the metal acting as the anode, and a highly conductive metal like stainless steel or aluminium serving as the cathode. This process causes oxygen ions to migrate to the surface of the metal, where they react with metal ions and undergo oxidation to form a thicker oxide layer. As more ions are deposited, the oxide layer continues to grow thicker. The anodizing time, voltage, current density, and bath temperature influence the thickness and properties of the oxide layer. Coloring. After anodizing, the porous oxide layer can be dyed or finished naturally for applications requiring a specific aesthetic. There are three methods for coloring anodized aluminium or metal parts. 1. Electrolytic coloring. The part is immersed in a bath containing metallic salts, and an electric current is applied. These salts fill in the pores, creating a strong coating that resists ultraviolet fading, but these colors are limited to bronze and black. This method is often used for outdoor and architectural applications due to its durability. 2. Dip coloring. The anodized part is immersed in a dye bath, allowing the porous oxide layer to absorb the dye. The depth of dye adsorption depends on the thickness and porosity of the anodic coating. The dyed coating is transparent, and its appearance is influenced by the basic reflective characteristics of the aluminium. There are many color choices within this method, but the color may not be very ultraviolet resistant, so it can fade over time. 3. Integral coloring. This third method develops color during the anodizing process itself. It uses organic acids in the electrolyte, and the color ranging from light yellow to black is determined by the alloy and anodizing parameters. The final stage of anodizing is sealing the pores to achieve a durable non-porous finish. This crucial step enhances durability and prevents corrosion by closing the pores of the oxide layer. The anodized layer can be sealed through cold sealing, mild temperature sealing, or hot sealing. Cold sealing. This process involves immersing the metal parts in a solution containing nickel fluoride at a temperature between 20 degrees Celsius and 30 degrees Celsius, creating a sealed layer of fluorocarbon aluminate. Mild temperature sealing. This method uses a nickel acetate solution at a temperature between 60 degrees Celsius and 80 degrees Celsius, offering a balance between effectiveness and energy consumption, while providing good corrosion protection without excess heat. Hot deionized sealing. Also known as hot water sealing, this method involves immersing the anodized parts in deionized water heated to 95 degrees Celsius to 100 degrees Celsius. The high temperatures hydrate the oxide layers, causing them to swell and effectively seal the pores. If sealing is poor or absent, the porous metal oxide layer can accumulate dust and debris. After sealing, the parts must be thoroughly rinsed to remove any remaining chemicals and dried to complete the anodizing process. Proper rinsing is essential for achieving optimal results. Types of anodizing. There are three main types of anodizing processes, each offering distinct characteristics and benefits based on the application's requirements. They are chromic acid anodizing, sulfuric acid anodizing, hardcoat anodizing. Chromic acid anodizing. Chromic acid anodizing, known as type 1, is utilized when a thin yet effective oxide layer is necessary. This process creates a thin film ranging from 0.5 micrometers to 2.5 micrometers, making it the thinnest oxide coating among the three types. As such, it is particularly suitable for decorative and functional applications. This method involves using a chromic acid solution, which penetrates the metal surface to form a protective aluminium oxide layer. Chromic acid anodizing offers excellent corrosion resistance without significantly altering the dimensions of the metal part, making it ideal for precision components. Its use is particularly advantageous on riveted or welded assemblies, where it is challenging to remove all anodizing solution, as it reduces the corrosive risk posed by sulfuric acid. Sulfuric acid anodizing. The basic operations for sulfuric acid anodizing are similar to those of chromic acid anodizing. This process is the most widely used due to its versatility and cost-effectiveness. Sulfuric acid anodizing involves immersing the metal in an electrolyte bath containing sulfuric acid, where an electric current facilitates the formation of the aluminium oxide layer. The process results in films that range from 5 micrometers to 25 micrometers in thickness, with 67% penetration into the substrate and 33% growth over the original dimensions. Due to its permeable nature, sulfuric anodizing is excellent for color dyeing and serves as a base for primers, bonding agents, and organic coatings. This method is commonly employed on optical and electronic components, hydraulic valve bodies, and computer electronics enclosures, because it is less expensive and takes less time to achieve the desired thickness compared to other anodizing techniques. Hard anodizing. Hard anodizing, also known as type 3, is a specialized process designed to produce a thicker, denser, and harder oxide layer, typically exceeding 25 micrometers in thickness. It is the densest and strongest type of anodizing. This process commonly uses sulfuric acid or its mixtures, and it is widely used in applications requiring high wear resistance, low friction, and superior durability. Industries such as automotive, aerospace, and military applications often rely on this process for parts that demand exceptional durability. The primary differences between the sulfuric acid anodizing and hard anodizing processes include the operating temperature, the presence of additive agents, the voltage and the current density used during anodizing. Hard anodizing typically maintains a low electrolyte temperature, between 0 and 10 degrees Celsius, and a low electrolyte concentration, 5 to 15% sulfuric acid solution, to slow the chemical dissolution of the oxide layer. It requires a high current density, which necessitates high voltages. These conditions can create localized temperature increases, making electrolyte agitation essential to prevent overheating. Without proper agitation, the combination of high current density and elevated local temperatures can significantly increase the risk of burning. In conclusion, anodizing is an effective method for enhancing both the appearance and durability of aluminium surfaces. However, various defects may arise during or after the process, often due to incorrect parameters or technical issues. Common defects include matte or rough surfaces, uneven coloring, cracks or peeling, thin anodic films, invisible acidic residues on the surface, and the formation of double layers. To prevent these issues, it is crucial to utilize the correct equipment and chemical solutions, as well as to have a skilled team. By managing these aspects effectively, optimal results can be achieved, extending the lifespan of anodized aluminium surfaces or metal parts. If you found this information useful, please like, share, subscribe, and turn on the notification bell for more content. Thank you for watching, and see you in the next video. Goodbye.